In this presentation, we're going to go through concepts related to performing a one-sample means T hypothesis test. Please note that this presentation is not meant to replace your reading of section 7.1.5 in the textbook. While watching this presentation, it would be very helpful if you follow along in the corresponding portion of the textbook. Lastly, please note that you are responsible for reproducing all parts of this presentation on paper according to our course guidelines for formatting of written work, except for any portions that appear in italics or any slides within the presentation that are specifically identified as not requiring reproduction. Before you watch this video, you should be familiar with all material associated with the sampling distribution of sample means, evaluating the two conditions requiring for modeling the sampling distribution of sample means, and the t-distribution, especially how to use our guru to calculate key values related to the t-distribution. In the presentation, we're going to discuss the mechanics of performing a four-step hypothesis test for a one-sample mean. The technique that we're going to use is the same four-step procedure we've been using since Chapter 5, that is prepare, check, calculate, with a null distribution sketch, and conclude. The steps are also at the bottom of page 258 of the textbook. You're going to need to reproduce all work associated with the example that starts on the next slide. So let's look at the problem statement we're going to use for our example, which is from the textbook. Is the typical U.S. runner getting faster or slower over time? We're going to consider this question in the context of the Cherry Blossom Race, which is a 10-mile race held in Washington, D.C. each spring. We first of all note, as a baseline, that the average time for all runners who finished the Cherry Blossom Race in 2006 was 93 and 29 hundredths minutes. That is about 93 minutes and 17 seconds. We're going to use that baseline to determine, using data from 100 participants in the 2017 Cherry Blossom Race, whether runners in this race are getting faster or slower versus the other possibility that there has been no change. Notice that that possibility would be what we would put in our null hypothesis. It represents the skeptical position. So using our typical four-step process, we begin with the prepare step. We're going to identify the parameter of interest, and I've gone ahead and shown that on the screen now. The parameter of interest in this case is the population mean, that is the average 10-mile run time for 2017. Next, we're going to go ahead and list hypotheses and identify the significance level, and then we'll close by identifying the sample mean, sample standard deviation, and sample size. So I'm going to go ahead and point out that we're going to come back to identifying the sample mean and standard deviation for the 2017 Cherry Blossom Race during the check step. Proceeding on, then we see that the sample size is 100. Our hypotheses in this case, using the average 10-mile run time from 2006 as our null value, is that the population mean for the 2017 race is equal to 93 and 29 hundredths for the null hypothesis, and otherwise the alternative hypothesis is that that population mean is not equal to 93 and 29 hundredths. The last part we need here is that we're going to assume a significance level of 5% for this hypothesis test. Next, we move on to the check step, where we're going to verify the two conditions to ensure that the sampling distribution of sample means is nearly normal. We begin with the independence check. The textbook mentions that the data came from a random sample of 100 participants in the 2017 Cherry Blossom Race, and therefore the observations are independent. Next, we move on to the normality condition, and we note that since the sample size is much greater than or equal to 30, we need only worry about whether there are any particularly extreme outliers. On the next slide, we're going to consider this further. So moving to the next slide, we make a histogram of the times for the sample 2017 Cherry Blossom Race data. And we notice that this histogram has a pretty bell-shaped type shape. In fact, we also notice that this histogram doesn't show any outliers of concern, and arguably no outliers at all. Therefore, we can say that the normality condition is met in this particular case, And because both the independence and normality conditions are satisfied, we can assume that the sampling distribution of sample means is approximately normal. Now, before we move on to the calculate step, in passing, I want to take note of the fact that the sample mean and standard deviation for the 100 runners in our sample from the 2017 cherry blossom race are 97 and 32 hundredths minutes and 16 and 98 hundredths minutes, respectively. Okay, now that we saw that both conditions in our check step do hold, we're going to start by computing the standard error. So I've shown the calculation work below for doing so. Notice again that we've replaced the population standard deviation with the sample standard deviation as an approximation. We get a standard error of 1 and 70 hundredths. The next thing I'm going to do is I'm going to compute the t-score using the formula for our test statistic t, capital T, and we see that the value for capital T is 2 and 37 hundredths. And the last thing I need to do is I need to identify the p-value with a null distribution sketch. So we now move on to the sketch portion of the calculate step. We're going to form a null distribution sketch, which we'll use to identify the tail areas of interest for computing the p, or probability value. Notice that I've started the sketch by showing the null distribution, normal distribution sketch portion, the two axes of the variable x bar and t axes. Minutes are the units for the x bar axis, and at the center of the null distribution sketch, I've put the null hypothesis value of 93 and 29 hundredths minutes. I then scale upwards 4 standard errors, and I scale downwards 4 standard errors, subtracting the standard error value as I move to the left until I have scaled my axes from -4 to +4 standard errors around the sample, around the null value. Continuing with our sketch, next we go ahead and include vertical lines going through plus and minus the absolute value of capital T on the sketch. We then go ahead and label the bottoms of those lines with those two values. Next, we're going to go ahead and shade the tail areas corresponding to the capital P, or probability value, and then we compute the probability value using our guru. Notice that in this case, the value was 197 10,000ths, or approximately 2 hundredths. Notice that I've also included on the slide what you would need to write on paper as what you did within our guru to find the probability value. I'm not going to show the our guru steps in this video, since I've already done so in previous presentations. Now, once we've computed the probability value, we identify it on the sketch by labeling half of it with each shaded tail on the sketch, since the probability value corresponds to the total area in the sketch tails. All right, the last thing we're going to do is move to our conclude step. In the conclude step, we're going to evaluate the hypothesis test by comparing the capital P, or probability value, to alpha and provide a conclusion in the context of the problem. So because our probability, or p value, is less than alpha, that is 2 hundredths is less than 5 hundredths, we're going to reject the null hypothesis. Therefore, the data provides strong evidence that the average runtime for the cherry blossom run in 2017 is different than the 2006 average. Since the observed value is above the null value, and we have rejected the null hypothesis, we would also conclude that the runners in this race were slower on average in 2017 than they were in 2006. And that concludes this presentation.